So, hello everyone. This is Michel Schildmeijer from the Netherlands. As you see in my background, I'm in my private jet, flying around every country. No, I'm in my home office. It's very warm in here. I don't know how it's at yours, but anyway, I'll try to make the best out of it, and I hope you enjoy my session. And my session is about security and containers in the Oracle Cloud, or any cloud or on premises, but yeah, because we talk about Oracle, I will focus on the Oracle cloud in general. First of all, some short story about me, if you're interested. I'm from Amsterdam, from the Netherlands. I'm so-called technologist slash architect from our company Quality, which is located in near The Hague in a city called Rijswijk. And I'm an Oracle ACE and an Oracle ACE director since the last year. I was nominated for Oracle ACE director, and I authored 2 books about WebLogic, one of my first loves when I entered the IT space. And my IT career actually started in 1994 with basic Unix. And the last few years are also focusing on container native and cloud native strategies, cloud native and container native platforms, DevOps, methodologies and strategies. So this is why I got into this subject about containerization and to extend that also the security around that. So the topics of today are a bit like this, maybe differ some in some of the topics, but the mainstream is containers and trends. What are we talking about when we are talking about containers? I'm going to talk a little bit about container runtimes. Also onto that about container security and container lack of security, maybe you can call it. And I'm going to tell you about the integration of containers into an orchestration tool like Kubernetes, which is the de facto standard for orchestration for containers. And I will talk about a little bit about the alternatives you can use besides Docker for building your containers and run your containers in a Kubernetes environment. So let's get started. If you look at container trends, then you can see that regarding to a research of Forrester, that containers are at this very moment, 2020. This is about 2019, but 2020 is some bit comparable due to all the COVID crisis situations. Companies got a little bit stuck. But if you look at organizations and companies who do containers, then you can see at this very moment, it's more or less 30%. And then I mean running in production as a full worthy, mature landscape for their application stack. And the prediction of Gartner in this is that it will predict that around 2022 and 2023, which is very soon in my opinion, and especially in computer and IT, it will rise up to 75%. So that's a huge transformation for companies to come from the standard situation where they are now to a more container native, container based landscape. And if you look at some major areas which companies and organizations are concerned of, is that you can see those 6 key areas in the right square. But number 1 is security and governance, because when going to the cloud or giving your applications to your customers, you need to have a good governance, a good security to meet all the requirements regarding privacy, GDPR, AVG in the Netherlands, that's the same actually. So it's very important to have a good security around your container landscape, and the security is divided in specific segments, which I will come to later. So if you look at container technology itself, there are a lot of buzzwords around it, sorry. So if you look at the evolution of containers, then you can see actually three major key areas: the bare metal platforms, the virtual machines, and next to that, containers. And in between, there's a lot of evolution going on. It's not that it's one step and then you're at containers, and one step down you're at virtual machines. In between, there's a lot of things going on, but in general, you can distinguish these three into these three major areas. So if you look at virtual machines before the containers became more popular, the prior approach for a company was to apply virtual machines. So you have one virtual physical server or a range of physical servers in your data center where you can run multiple applications or databases or any other environment you require. And these were all divided into isolated virtual machines, actually using some kind of a virtualization technology. And all these virtual machines were isolated from each other, so they were sharing the hardware resources, but for the rest they were isolated, and they didn't know anything about any other virtual machine. So they were running independent of the other virtual machines running on that hardware in that specific data center. So in contrast with container technology, the server runs a single operating system, and each application is able to share all these things on this operating system. All the libraries which are running on an operating system in a virtual machine are not specific for an application, but usually it comes with a distribution. If you look at Linux, with a distribution of packages which you maybe require to install an application or an application server or a database. So if you look at containers, for instance, if you look a bit beyond virtual machines, then you come to containers, and containers are set up to accomplish work in a multiple container architecture, like a cluster. And you have several terms and definitions regarding containers, such as namespaces, profiles, C groups, which are all similar to what a VM does. But the main thing is that containers are sharing the kernel on a bare metal platform. So there's no virtualization in between. There is some, but I will come to that later. But if you look at containers, they are they're isolated packages of application configuration managed by a orchestration platform, which manage networking, which manage compute power, which manage security, specific for a container or a set of containers. And within this container, you only need to have some additional libraries to run your piece of application in that container, and some binaries maybe, but not an overload which you can have in a VM. So this means a container can be very lightweighted. So if you look specific at a container running on an operating system, then you can see it runs as a process. If you look at Linux, which is the base platform for containers, then you can see every container which you start up using Kubernetes or another orchestration tool like Docker Swarm or some other, then you can see it runs as a process, and this process is isolated, has an isolated workspace, but share a piece of the kernel with the other containers running on that platform. The containers themselves, the images are packed software which you can store somewhere in a repository, and you can pull it out if you need it and start up a container. And you can also do lifecycle management and everything on that. And there also starts the insecurity of containers. Right. So if you look at some ancient container stacks, then you have this container technology was already there ages ago when Unix got commercial during the beginning of the 80s of the previous century. The container was already there, actually. The prerequisites for a container was already there. So if you look at the first concept of a container, which was called chroot, it was a concept where you could start up a process, and this process was isolated, used an isolated piece of the file system within Linux, and this file system was only, Unix, this file system was only given to this specific process. So the first step to isolation was already there, and you could also isolate some disk space to this. And this option was later added to some other Unix distributions like FreeBSD. At that time it was called jail containers, and this was actually an extension of what the pre-containers era was using with chroot. At that time, containers weren't that popular, so actually the feature wasn't used that much. But if you go look any further in the evolution of containers, then you had several other initiatives like Solaris containers, process containers. But at the base of the current containers, so in the present time, Linux containers is one of the things which were the basis of Docker-based containers, and also the Open Container Initiative, which all the containers from nowadays are complied to. So Linux containers and also Clear containers, which is in fact a pre-version of what I'm going to discuss later about Kata containers. Clear containers was an initiative from Intel. Intel developed an initiative to isolate containers more and more like a VM, but still have the correct characteristics of a container, which we'll come to later. So if you compare containers to virtual machines, then you can see some key differences, which I already discussed a little bit. But the main difference is that a container, in the opposite of a virtual machine, is using the kernel by a hypervisor, a piece of software, a sort of a driver, which translates everything to the core operating system, and the core operating system translates it back and gives the input and output to the guest VM. But on top of that, the VMs themselves also have a kernel, and also run as the same as the core OS operating system. But this makes it possible for a guest VM to run its own operating system, unless you have the right hypervisor running on your core OS. So if you look at containers, then you have your dedicated hardware servers in your data center. You have your core operating system, which usually is Linux. And on top of that, you have a container engine, and this container engine translates everything for your container. And on top of that, you can run your container with your configured application and all the necessary binaries and libraries, and a piece of an operating system, a very lightweight, like Alpine, for instance. It's commonly used to run a container application. So if you look at traditional application architecture and flow, so you have some risks for that, which you can identify for that. So you can see here the typical architecture for the components to build a container from development, test, into production. You can see in here the developer is building the container, is testing it with some scripts, and is pushing it to a registry. It can also pull, he or she can also pull a container from a registry. This registry can be either public or private. It depends on how you're, what you need. And then if it's built in this whole pipeline process, it can be a DevOps pipeline or maybe manual. It depends on how your processes being executed, the administrator pulls the container from the internal or external registry and deploys it through an orchestrator. This can be an automated process, but as I already said, can also be a manual process. It can push it to the orchestrator, and the orchestrator will schedule a container somewhere on a host. You don't know where, because it can be everywhere. The scheduler decides where you will deploy it, unless you apply some labels or selectors in your configurations. So in all these stages, you can see some risks, image risks, for instance. If you look at image risk, well, images are actually effectively static archives. So it includes all the runtime configuration of a given application component. So this image will be stored somewhere in a registry, and it will miss some security updates, some critical security updates, some vulnerability updates. So these container images can get outdated without you knowing it. So you have to be aware of, when you push your images to your registry, to have a good lifecycle management also on your registry. So you need to have an update process in your container image registry to update your containers. Another thing which you can package within these container images are maybe packaged malware from outside, or packaged text files with unencrypted passwords, which can be expose an image risk. So these are all considerations which you have to think of when you build your images and push them to a registry and store them over there. So if you look at the registry, the container registry itself, to push an image to a registry requires a secure connection. So you have to be aware of that your connection to your registry is secure. It shouldn't be sensitive to any outside attack of a hacker. You should not use embedded secrets in your containers, so keep them out of that. And also you have an increased risk of something like a man-in-the-middle of attack, which some outsider can intercept this action. So you have to be aware of to encrypt your connections very well. And also, I already told about the images, about stale images. They can pose a threat with all the vulnerabilities when you store it in your image registry. Another thing is that you also push images to a registry, and it can contain all kinds of sensitive data, insufficient authentication and authorization requirements in your image. So this is also a risk you should identify and compromise into your registry and be aware of it. So the next thing to be aware of is the orchestrator. So a platform like Kubernetes, which is an orchestrator, and is well, I may call it the de facto standard for orchestrating containers. You can have unbounded administrative access if you don't apply the necessary security measurements within your orchestrator, like network policies, like role-based access controls. So if you make use of service accounts, which is typically for an orchestrator like Kubernetes, then you have to restrict access to those service accounts so that everyone can access all these service accounts, but limit access to that with restrictions. Only grant permissions for specific applications for developers or testers or any other persona which needs access to that. So you need to be aware of all these risks within your orchestrator. And the last one, which I will focus on today, is the host operating system risk. So containers are typically using data storage volumes, are running on a data center in a host. You have to be aware of that the service attack on a host can be very large. Depends on where your host is. In all these vulnerabilities in your applications, which are maybe not being identified or be diagnosed, you have to be aware of that. Any attack on your operating system can impose your entire cluster of containers running over there. So if a hacker managed to get into your operating system where your Kubernetes master is running, then you're really doomed. You can they can do everything what they want. So you also need to be aware of that they can tamper your operating file system, and they can access certain kinds of components of your Kubernetes or your container cluster. So these are all kinds of requirements for having a secure container landscape. And I want to focus on this host operating system thing where containers are in fact running, as I already said, as a process. So these are the topics I already discussed, weaknesses and uncontrolled network access. All these things I already told about. User access rights, improper user access rights, for instance. So if you look at the shared kernel risks, which is one of the majority risks on a host operating system, then you can identify this as the risk, which is maybe the highest risk at all from all, because the operating system kernel itself, it's the core of your operating system. So if it gets destroyed, it doesn't have to be that they steal data, but just destroy it, then your entire cluster can be gone within a blink of an eye. So what can you do about it? You can run like this usual default setting, which a lot of organizations use when they start with a container-based landscape using Docker software as the container engine software, using containers within each own namespaces, but still sharing the kernel, running a system process, and the system process is isolated and permitted to use some storage and operating compute power and some memory, which you can set on a quota or on any other method how you can do that. But in here, the kernel is shared. The isolation is only based on namespaces. So if you look at a new concept, well, new, it's about 2 or 3 years old. You can also think of isolating the kernel and take it within the container instead of taking it from the host operating system. So in fact, what you have is a container with all the characteristics of a container. So it's lightweighted. There are not many. There's no overhead on software in it, but it's running as a virtual machine and it has its own kernel. And for your host operating risk, this is a major improvement of your security, because when a container is affected by hostile attack, then it's not your entire cluster will be affected, because this kernel is isolated. Still runs as a system process, so it has all the things and the requirements and the basics of a container, but it runs as almost like a virtual machine. So if you look at some alternatives to run a secure container technology stack, then if you look at some layers within this container technology stack, then you have some default container runtime engines, builds and everything, build tools, and you have some alternatives. If you look at the engine, so running a container as a process and using it as the API and translate it and implement it into your Docker cluster, your Kubernetes cluster, then you can run Docker as a daemon. But you can also use another daemon like containerd and use Cri-o as a runtime. Cri-o is another open source initiative, which I will come to later. So if you look at the runtime, so the translation from your Docker layer engine to the process which is actually running, you can use a traditional run C, which is also OCI compliant, or you use Kata Containers, the isolation in here. If you look at building and all those kinds of things, you can use the default Docker build software, or you can use Podman, and Podman can be rootless. You don't need to be root to run Podman commands, which is different with Docker. And for building and also for searching for registries, for building containers, you also can use Builda, which is another open source initiative. And for search images through Docker registries or container registries, you can use Scopio, which is also an open source initiative. So you can make your container landscape, but all the tools around it, you can make it more secure by migrating some of these stuff or trying it out. And you can see that Podman, for instance, is very much similar in command line, everything to Docker. So if you look at the isolated container VM, I will call it, then the technology around that is called Kata Containers, and Kata Containers is an initiative which came out of Intel. I already told that with Clear Containers, Intel Clear Containers, and now Red Hat is heavily investing in it, but also Oracle supports Kata Containers on their cloud infrastructure. So you can run a Kubernetes cluster running with Kata Containers using another container runtime interface for your Kubernetes, like Cri-o, containerd, or Fracti, which is another container runtime, on your Oracle container infrastructure. So if you look at Kata and container, if you look at traditional Docker-D daemon, Docker-D starts up the process. It connects with all kinds of bridges and APIs to your container. The container will start as a process on your operating system, and run C is in fact actually the Kickstarter to run your container. But you can also run a similar version of run C, which is called Cri-o, and Cri-o is also a container runtime interface, which is which meets the standards of the OCI, more like Docker. Docker was, in fact, when it was launched, or in 2014, I think it was, Docker is, of course, a commercial party, also contributes to the open source, of course, but it, in essence, it's a commercial party. So the Linux Foundation and the Cloud Computing Foundation also search for more open source initiatives to run your containers. So if you look at alternatives, then you can run your containers with Cri-o containerd, and to run this you can use containerd shim, and shim is a process which takes care of all the input and output of your container, and also translates all kinds of command instructions from your container to Kubernetes, for instance, and the way back, and all the input output written to logs or everything of standard out of your console are written and picked up by your shim process, which is a very lightweight process to use. So if you look at a diagram of it, you can look at the traditional Docker shim, which is running with run C. Docker is compatible with containerd as well. So containerd is in fact the daemon, and Docker engine will run with the shim version 1 to start up a run C process to run your container, and Kubernetes will pick that up and create a container and use a pod in a pod. Sorry. But if you look at Kata Containers, then you have another version of shim, and this shim is, in fact, if you look at Docker containers, Docker-based containers, then every container needs its own shim, and with shim version 2, I draw it here a bit faulty, because in fact, if you run Kata containers, it uses only one shim process, which is running all these Kata runtimes within. So it's more simplified, and you don't need any proxy within, because the Q proxy will take care of that. So another thing is, I talked about isolation of containers, and if you look at isolation of containers and talking about virtualization, then you need to have some kind of a similar approach to what virtual machines are. So if you look at traditional virtual machines, they use hypervisors. So you have the physical layer, and in between you have a hypervisor like Hyper-V or Zen or VMware ESXi. And on top of that, the VM is running with the guest OS and all kinds of application stacks and databases and everything. And if you look at container VMs in this case, then you have also some thing called like a hypervisor. In this case, it's KVM, and KVM is also the hypervisor Oracle now supports for its own infrastructure. So if you run an Oracle infrastructure, if you have a database appliance or run it in the Oracle Cloud, then the hypervisor which is used to start up a VM is KVM. So also for containers, Kata containers, KVM is the base layer for hypervisor for Kata containers and isolated containers, but also you need some extra layer on top of that, and this extra layer is an emulator, and this emulator works together with the KVM and emulates, in fact, a virtual machine to a container. So in fact, that's the difference with the traditional VMs. So it can be lightweighted as a container. So if you look at it, the emulator is used for Oracle and for a lot of other isolated containers. It's used QEMU or NEMU. These are all open source initiatives. And you also have Firecracker, and Firecracker is some sort of a micro VM, a bit similar to QEMU, but it's more lightweighted, but the security restrictions are a bit more loose than using QEMU. And Firecracker is used in if you use AWS and you use the Kubernetes engine over there, they use Firecracker if you use isolated containers over there. So some of the prerequisites to run isolated containers, and in special Kata containers using this QEMU emulation, then you need to be aware that your host operating system, your host system can implement or supports virtualization, and you can easily look it up to see the CPU flag VMX. If it's enabled, then it's you can run this on your system. If it's not, then you need to enable it in your BIOS. So not every system is equipped to use and to run virtualized isolated containers. So if you look at our container runtime for Kata, the thing is, if you run the Oracle Container Runtime, so the Kubernetes engine in the cloud, the managed Kubernetes engine, the current versions are still running on the Docker-based containers, no isolation. So if you use the managed Kubernetes engine, so you still stick to the old Docker implementation. But when you when you roll out an IaaS platform, so some VMs in your cloud, and you start up your Kubernetes managed server by yourself over there, then you can run with Linux 7 or Linux 8 and your Kata container, you can, and your Kubernetes cluster, you can run a fully isolated container runtime landscape. So this is a bit about this Kata container architecture. On the left, you see your Kubernetes cluster, and on the right, you can see the Kata container running there. And this Kata container is running inside a pod, of course. Kubernetes used the concept of pod, and this pod is running a container or sometimes multiple containers if you configure that. in that manner. But if you look at the Kata virtual machine, then you can see its own namespace isolated from the rest. And this namespace uses the kernel, of course. And in this Kata container, you have a small agent which is communicating through gRPC with the container cluster, with the Kubernetes cluster. And this gRPC connects with the shim and the runc to get the input-output of the containers and the application within your containers, and also it executes all kinds of commands through the layer. So supported for the Oracle Cloud at the moment. I already told you the Oracle Cloud infrastructure is supported. Also Oracle WebLogic, for instance, you can run Oracle WebLogic on isolated Kata containers. And also Oracle database, you can run them in containers. Although I had a discussion with my colleague DBA who doubted to run Oracle databases within containers. I disagree with him because it can be done and can be useful, but yeah, there are some things to be done to make it more efficient to run Oracle databases in a container. Although I have a short demo at the end of my presentation to prove to you that Oracle database can perfectly run in a container and in an isolated container in a Kata container. So all the additional toolsets which I already mentioned, Pubnum, Scopio, Builda for building and searching through the container registries. So my shopping list for when I set this up was, of course, a cloud compartment for the cloud infrastructure, a few VM instances, 3 regions. I took a very simple Kubernetes cluster. I built it up very simple, so 1 master, no high availability, and 2, the bare minimum actually for a Kubernetes cluster, 2 worker nodes, and some basic Docker and Kubernetes setup. As I already said, Docker and the OCI compliant technologies are very much compatible, so you can run and use them all both together actually. So if you have a container landscape based on only Docker implementations, then you can easily migrate them to isolated containers without doing a big bang scenario, for instance. So, well, these are some prerequisites to run your container. You need to download some extra software. If it's not in your VM present, you need to enable KVM, for instance, and you need to install the Kata Runtime and the container runtime interface for your Kubernetes. So this is the Docker integration. So you can tell to Docker, the Docker software, if you run Docker software, to run the Kata container or containerd runtime instead of a Docker runtime with these simple commands to tell to the Docker daemon that you have to use another C group driver. And the standard C group driver within Linux, which is used by Docker, is C group FS, but you can also instruct Linux to use it from a system perspective, to use systemd in this case. You still need to have a storage driver to translate, to use all the volumes and the volume amounts within your containers and store them somewhere on your shared disk or on disk on your server. And you have already told you you have to install a CRI compatible runtime to run Kata containers in your Kubernetes engine, Kubernetes cluster. So a little bit about Kubernetes, some of the few very basics. Then I'll go on telling about the integration of Kata containers in Kubernetes. So if you look at Kubernetes clusters, Kubernetes is an orchestrator, and it's a set of APIs to communicate and to instruct and to schedule and then to orchestrate, however you call it, containers in your infrastructure. If you have 5 or 6 containers, then it's manageable and to do it by hand. But if you have a production system, let's say you have 10 servers with maybe 20 Kubernetes clusters running, 100 containers running, then it's totally unmanageable to start up all these containers using scripts and everything, assign network, assign routing, everything, assign storage and everything, to do that manually. So you need to have some extra layer in between the orchestrator, and in this case it's Kubernetes. You have to use it to run this all. So if you look at the basics of this Kubernetes container orchestration platform, then you have your container engine, which is just the container software, the runtime, as already discussed. You have your master. You have one master or several masters, and this master is running somewhere in your cloud. It can be multiple masters. If you do an HA setup, an high availability setup, then it's advisable to run your master in several availability domains. So several duplicates of your master running in several availability domains. And your master consists of a few components. There are a lot more, but these are the main components. You have your API server. So in fact, the main port for everything, for exchanging all the information which your Kubernetes cluster uses. You have your scheduler, the default scheduler within Kubernetes, or you can write your own scheduler, the kube controller, and the etcd. So etcd is a key value store which holds all the cluster configurations. The controller is being used to control everything with your kubelets on the remote nodes. So if you look at the nodes, you have a master node and you have several worker nodes. In my scenario, I had 2 worker nodes. You have your kubelets and your kube proxy. Your kubelet is in fact for lifecycle management of your pods. It reads manifests of your pods. If you have like static pods, which uses a manifest file on your host where your pods are running, then the kubelet looks into these manifest files, or it watches the lifecycle which it gets from the master node. And with that, it can communicate with the pods which are scheduled on a worker node. And then on top of that, you have your pod running with several containers within it, or one container, depends on how you configure that. And then you have your interface, your administrative interface, maybe a Kubernetes dashboard, a graphical dashboard, or a command line interface kubectl. So here are some specific topic explanations about what these components are all like to mention servers, for instance. Servers is in fact a communication definition between within your Kubernetes cluster to communicate. So if you have a pod using a database, then it can run without the servers, but then you can't access it unless you access the pod itself. So you have to set up a service where you can expose a port like the database listener port to an external IP. So it can connect to an application, for instance. So if you look at the runtimes and Kubernetes, and in special the Kubelet, Kubelet is already told responsible for the container lifecycle. So every Kubelet is installed on every node in the container orchestration landscape. The Kubelet instructs the runc through a container engine software, and in this case it can be Docker or containerd, and it instructs through runc with the OCI compatible runtime interface to start up a container, and in Kubernetes terms it's to start up a pod. And the alternative, which I emphasize more, is to run it with containerd and Cri-o and start up an alternative container runtime with Kata containers. And this initiates that a pod will start up a virtual container, a virtualized container, sorry. So if you look at this runtime interface, the OCI interface I already told you about, and you see here, right, the container runtime interface, which Kubernetes implements to run containers from other flavors than only Docker-based containers. So to prepare to do the requirements, the preparation of requirements of your Kubernetes cluster to run these Kata container and these virtualized containers, then you need to do some things. You need to install these packages, which I already told you, and you have to instruct your kubelets to use the proper container runtime. And you can do several approaches. If you have already a running container cluster, then you can take a node off one by one to decommission the node from your cluster, to uncordon, it's called, and then you can change your kubelet interface to run, instead of the Docker and run C interface, to use your containerd or Cri-o runtime interface. So you can do it one by one, or you can build up an entire new interface and install your images again in your containers. For that, you also need to have persistent volumes, because if you run a database and you have some state in your database, you don't want to destroy all that data and get lost of everything you had. So it's always to be aware of that. You have to have something like a persistent volume to store all the data on, especially for databases. So this is a bit of the preparation things you need to do. You can use the Cri-o runtime in this case, so you need to be aware of the Kubelet service which is running on the system to make use of the Cri-o configuration. So you have to put in some extra arguments which the Kubelet as a process running on the system can pick up to run another endpoint for your containers. In this case, it will be the Cri-o, but you can also run the containerd socket. But you need to be aware of, if you do that, then you have to specify that your pod network interface should be always match some kind of a DNS range within these IP ranges. So your containers know and can be assigned by the kubelet and by the kube proxy to the proper IP addresses. So in this example, I instructed the master to use another runtime interface using containerd. And then I have also had to notify the container, the master to use containerd as the container runtime. So if you look at the example of this, then you can see if you do a kubectl get nodes and you do a wide configuration, and you can see the container runtimes differ. Some of them are using Cri-o and some of them are using containerd. And they can coexist to each other. So the alternative tool already told you, you can also use Podman. But if you did do that, then you're at the basics. But still, if you start up a container, it still uses the same kernel as any other container. So you need to do something extra in your Kubernetes cluster to instruct your cluster to use container isolated VMs. And for that, you have to be aware of and use a runtime class. And this runtime class was introduced in Kubernetes in version 1.11. And you can, with a specific option within Kubernetes, a label, you can label your pod to run this runtime class. So if a pod starts up and starts up a container, then the pod knows it should use its runtime class, and in this case, it's the runtime class to use the QEMU hypervisor from KVM. So you have to label also. You can label pods to schedule, label nodes, to schedule pod specific nodes. So you can use node selector in your Kubernetes cluster to label pods with a QEMU and Kata to run on a specific node. So if you want to have dedicated nodes only to run Kata containers on in terms of migration or isolation, maybe test development run on Docker and production run on Kata, then you can separate these from each other. So here you have an example of your a YAML file to implement your Kata runtime class. And this labeling permission to label parts for specific nodes, you have to apply that on this YAML file. And on top of that, you have to label your nodes to make use of this Kata runtime. I will show this in a demo later on, so you can look at that. And there you can do a kubectl to show the labels of your nodes, and there you can see two of the nodes are labeled as Kata runtime. And to be aware of your Kata containers, to run Kata containers to your pods, you have to implement the runtime class to your pod definition file or into your deployment file. In this case, it's the deployment file, deployment definition. But if you run a pod without a deployment, then you have to specify the runtime class within your pod definition. And to see if your container is running real-time Kata, you can do a PS on your node where it's running. And there you can see the QEMU virtualization process is started up. So in this case, it's a proof that Kata container is running this specific container. Kata is running this specific container. Sorry for my English sometimes. So in this case, you have proved that the container is running within an isolated virtual machine, but still as a container. So, so at last, I'd like to give a short demo of how it works. So I hope you enjoy it. Just a minute, I have to stop this thing and reshare my screen, or maybe you can see it. No, I don't think so. Hang on a minute.
At the moment, we see your full screen.
Yeah, okay, thanks. Let me see.
There's just one question waiting in the Q&A section for afterwards.
Yeah, thanks. Let me see. New share. And here. Okay. So here I have a Kubernetes cluster running on the Oracle Cloud Infrastructure, and hope everyone can see it. If not, let me know. It's running 3 nodes, so KVM Kata 1, which is the master node, 2 and 3. So if I do a command like kube, I've created an alias for kubectl to K, so it limits my time for typing because I'm very lazy, of course. Then you can see here they are running Cri-o. So the Cri-o runtime is running, and if I do a show labels, then you can see I've labeled one node to run Kata, and it's node 3, and I've labeled one node to run containers without the Kata runtime. So I've prepared 2 YAML files in here. One is I would like to take an example of an Oracle database. So I took an Oracle, very simple setup of an Oracle database. I have 2 YAML files. One YAML file uses non-Kata, and one YAML file uses Kata. So if you look at the non-Kata, then you can see, sorry, that I commented out, I hacked out the Kata runtime class. So if it starts up, it won't use the QEMU KVM hypervisor. It will start up as a usual process. So I will apply this one, this deployment, deploy -f. My tab's not working. Okay. Oh, sorry. I made a mistake. So the deployment has been created, so the pod will run. I've assigned a specific namespace for that. Let's say RLDB namespace Q. Sorry for my typos. So it's running over there. And if I do -o white, then I can see where it's running. So it's running on node 3. And why is that? Because I deployed an Oracle Kata. So if I do a Kata container, if I do a QEMU, then you can see in here, the Oracle database is running with the QEMU virtualization. So if I do the non-Kata thing, I'll do it again with the non-Kata. So in here, there's no QEMU Kata runtime class applied. So if I do again, so it's running on KVM Kata 2. And if I run here the same command on the Kata 2 version, Kata 2 container virtual machine, it's not running. So it's only running the database itself, container. You can see it in here, it's running, but no Kata containers. So that's in fact the proof that you can run them separately with the proper labeling and proper node selectors applied to your deployments. So that's about it. That's what I wanted to prove, and I heard there's some of questions with the Q&A, so I will look into that.
Yeah, there's one Q&A.
Yeah. So the question is, with your background in WebLogic, would you run a prod WebLogic in containers, Docker, for example? And what about Oracle tools on top of being WebLogic? Yeah, that's a good question. At the moment, Oracle supports to run in containers and running Kubernetes, and they have an excellent GitHub repository for that. But it's still in development, and it's still the question if you really want to run such as heavy containers from a container perspective, as WebLogic could be, in a container native landscape. It can be done. There are several options. You can use a layered image structure where you build image on image on image. So you have an operating system image like Linux. You have an WebLogic binary image. You have a WebLogic domain configuration image, and on top of that, an application limit. So it can be done. And from a perspective of delivering infrastructure, I would sure say yes. But if you look at more if you look beyond that, so in terms of monolithic versus microservices and everything, serverless and all those things, then WebLogic is of course not the de facto platform to use within containers. So from a infrastructure DevOps perspective to infrastructure as code perspective and everything, then I would say yes, although it's not mature yet. Yes, you can run it, and I would, yeah, I could advise it. But from the other hand, if you focusing on the microservices strategy and yeah, more to the future of your application and component architecture, then I would say just wait a little while and yeah, just try and test and let's see what Oracle does with it. So that's my answer, in fact. Okay, thank you very much, everyone.
Thank you so much.